Have you ever stopped to think about how we can describe any location in the universe with just two numbers? It's a simple, elegant idea that became the absolute foundation for everything from your phone's GPS to the video games you play. So today, let's map it all out. It all starts with a really simple, almost kind of silly question. Picture this. You're lying in bed, just staring up, and you see a fly on the ceiling. Now, if you wanted to tell someone its exact location, how would you even do it? Well, this very problem, this fly, sparked one of the biggest breakthroughs in the history of mathematics. So the guy puzzling over this was the 17th century French philosopher and mathematician René Descartes. And the story goes that while he was watching that fly, he had this incredible aha moment. He realized he could pinpoint its position using just two measurements, how far it was along the ceiling's length and how far it was across its width. A simple observation that would literally change the world. That little insight gave birth to what is basically a mathematical map. So let's build it. Right now. We're going to do it piece by piece, just like Descartes imagined. And trust me, it's way simpler than you might think. All right, so every good map needs a starting point and some directions, right? For our map, we just draw two lines. First, we've got a horizontal line. That's our side-to-side movement. We call it the x-axis. Then we draw a vertical line for up and down movement, and we call that the y-axis. Now, the point where they cross, that's our starting point. It's our ground zero. We call it the origin, and its address is simply 0, 0. So how do we give an address to any other point on this map? Well, we use something called an ordered pair. It looks just like this, x, y. The first number, the x, tells you how far to walk along the x-axis, and the second number, the y, tells you how far to go up or down on the y-axis. And here's the most important part. The order is absolutely crucial. The point 3, 5 is a completely different place than the point 5, 3. And hey, if you want to sound like a real math pro, you can use the official terms. The x-coordinate, our horizontal position, is called the abscissa, and the y-coordinate, our vertical position, is called the ordinate. So in any ordered pair, you always state the abscissa first and then the ordinate. Okay, so we have the map and we have the addresses. Now let's learn how to actually read this thing and navigate its different regions. So you see how our two axes slice this whole infinite flat surface into 4 distinct sections? Well, we call these quadrants, and they're numbered 1, 2, 3, and 4, starting in the top right and moving counterclockwise. Pretty simple, right? Now, this system gives us a really simple cheat sheet. In quadrant 1, both your x and y numbers are positive. If you move over to quadrant 2, your x becomes negative, but the y stays positive. Then down in quadrant 3, they're both negative. And finally, over in quadrant 4, x is positive again, but y is negative. So just by looking at the signs of the numbers, you immediately know which region of the map you're in. But here's where Descartes' map gets really powerful. It does more than just plot static, lonely points. Its true strength comes from connecting them to form lines, which can tell a whole story about the relationship between those points. So whenever we draw a line on this plane, it often crosses our main axes, and these crossing points are really crucial landmarks. The spot where the line hits the x-axis, that's the x-intercept, and where it hits the y-axis, you guessed it, the y-intercept. They're key coordinates you need to understand any line. Okay, but what about the steepness of a line? Is it a gentle hill or a steep cliff? We have a word for that, slope. It's just a simple ratio that tells you how much a line goes up or down for every step it takes to the side. We figure it out by taking the rise, that's the vertical change, and dividing it by the run, the horizontal change. Rise over run. It's the secret code for every single line. And it turns out there are really only 4 types of slope. First up, positive slope. If a line moves up as you look at it from left to right, it's like an uphill climb. That line is increasing. Next, if the line moves down from left to right, well, that's a negative slope. Think of it like a fun downhill slide. The line is decreasing. So what happens if a line is just perfectly flat? A horizontal line has 0 rise, right? It's not going up at all, so its slope is just 0. It's like walking along a perfectly flat horizon. And now for the last one, the real oddball of the group. A perfectly vertical line is all rise and no run. And since you can't divide by 0 in math, it's a big no-no, we just say its slope is undefined. It's like a sheer vertical drop.
Now, using slope, we can describe exactly how lines relate to each other. Parallel lines are like train tracks. They have the exact same slope, and they will never, ever cross. Perpendicular lines are the ones that meet at a perfect 90-degree angle, like the corner of a square. And their slopes have this special relationship. They are negative reciprocals of each other. So we've built this whole mathematical map, but you might be thinking, okay, cool, but this is just some abstract idea from the 1600s, right? Well, no. Descartes' legacy is, quite literally, in your pocket and all around you every single day. See, the true revolution, the real genius of Descartes' work was this. He connected two worlds of math that had always been separate. For the first time ever, algebra, the world of equations and numbers, could be used to describe geometry, the world of shapes and space. An equation could suddenly become a line, a circle, or a beautiful curve. It was a complete game changer.
And this idea was just the spark. Another mathematician, Pierre de Fermat, was working on similar ideas at the same time. And a little later, giants like Isaac Newton and Gottfried Leibniz grabbed this coordinate system and plugged it into their brand new invention, calculus. That allowed them to map not just position, but motion and change itself. So why does any of this matter to you? Well, the GPS in your phone uses a coordinate system to find your location. The amazing graphics in your favorite video game? That's just millions of points plotted on a coordinate plane. Engineers, architects, designers, astronomers, they all rely on this fundamental system to design our buildings, map the stars, and build our entire modern world. Which kind of brings us right back to where we started. A simple, everyday observation of a fly on a ceiling gave us a way to map the entire universe. It really makes you wonder, doesn't it? What seemingly small, everyday problem that you notice today could be the seed for the next world-changing idea?